right, let's jump into our third type of symmetry. We'll start with an example. Let's sketch a graph of x squared plus y squared equals 16. Now, this is also going to be a circle. Notice we've got the x squared and y squared terms. It's going to be centered at the origin because there's nothing being subtracted from the x or the y. And because 16 is the radius squared, that means the radius will be 4. So we need to draw a circle centered at the origin that has radius 4. Okay. So, it's not the best circle in the world, but it'll do. Now, I want to point out something that is not relevant to what we're going to be looking at, but that you might have noticed. This does have symmetry with respect to the y-axis and the x-axis. If we look, there is symmetry about the y-axis, and then also about the x-axis. That happens to be true. But what we're looking at right now is going to be unrelated to those. We're going to look at a third type of symmetry, and this is symmetry with respect to the origin. Now what this means is if we have a point x comma y that is on the graph, then the point negative x comma negative y, which is reflected across the origin, will also be on the graph. What this means effectively is that if we've got one point on the graph and we go through the origin and then we go an equal distance in the other direction, that other point is also on the graph. Now, the other symmetries had a property that said the graph was unchanged if we reflected across the x-axis or the y-axis. We're going to have something a little bit different here. In this case, the graph is unchanged if we rotate 180 degrees about the origin. That is interesting. We're rotating now instead of reflecting. Now here, if the point x comma y is included in the graph, then the point negative x comma negative y is as well. And we do have a test here, just like the other ones had tests. The test says if we replace x with the opposite of x and y with the opposite of y, both of them are getting replaced with the opposites, we end up with an equivalent graph. So we can test that out here. If we take the original equation and we replace x with negative x and y with negative y, we end up with, again, a negative times a negative is a positive, so that becomes positive x squared plus y squared equals 16. All right. I actually want to look at two more examples of graphs that have this type of symmetry. We're going to go through them a little quickly because I don't want this video to be too long. And the second graph is probably one that you've never seen before, but I think here it'll be good to do two more examples instead of just one. So let's jump in. Let's sketch a graph of y equals x cubed. All right, y equals x cubed. I'm going to make a table of values here really quickly, x and y. I'm going to pick -2, -1, 0, 1, and 2 here. And then for y, I'm going to start with 0. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. And then -1 cubed is going to be -1, and -2 cubed is going to be -8, because a negative times a negative times a negative ends up being negative. And I'm going to plot these points. -2, -8 is going to be here. -1, -1 is here. 0, 0 is there. 1, 1 is there. And 2, 8 is up here. Now, if we had all the time in the world, we would plot more points and we would get lots and lots of points so we could see very carefully what's going on. But because we don't have all the time in the world, I'm just going to show you what the graph looks like. It's going to be a smooth curve, looks something like this, and it's almost a parabola here with the other side going in the opposite direction. It's not actually a parabola because parabolas have very specific geometric properties, and this is different. So I don't want you to think that it is, but it does go up similarly to how a parabola is on the right. Just on the left, it goes down instead. Now, if we want to test to see whether this has the right symmetry, I mean, first of all, you can kind of look at it. If we took this curve up here and we rotated it around 180 degrees, we would get that curve down there. So by inspection, it looks like it has the symmetry that we want. But if we want to test it, we replace y with -y. We replace x with -x, and we get this equation. Now on the right, a negative times a negative times a negative is still negative, so we're going to end up with the opposite y. The opposite of y equals the opposite of x cubed. But now what we're going to do is we're going to divide both sides by -1, and that gives us positive y equals positive x cubed, which is the original equation. So we can check this algebraically and see that this satisfies the property that we want. Now, unlike the last example, this is not symmetric about the y-axis or about the x-axis. This is only symmetric about the origin. So it was a coincidence that this one on the left happens to have all three types of symmetry. Now there's one more graph I want to show you, and we're just going to take a very quick peek at it. This is going to be y equals sine of x. Sine is abbreviated SIN. If you have never seen this before, don't feel bad. This is something you're going to encounter in trigonometry. But what I'm going to do is I'm going to draw a very quick sketch of this graph. It's not going to be the most accurate. I'm just doing it by hand, and this is difficult on the iPad because there's not much friction with the pencil, so it's hard to draw a very, very super excellent graph. But I'm going to give it my all. And sine, I'm not even actually going to label the tick marks on my x and y axes because I don't want to worry about that. Sine is a graph that looks something like this. It actually repeats itself over and over again. All right, it's just a rough sketch. It's certainly not perfect. Honestly, I think the best part is this part right here, because it's supposed to be a nice, smooth curve kind of going up and down, almost like if you took a slinky and you were to kind of pull it apart and extend it, it would look something like this. Anyways, this is a graph that you will encounter when you take trigonometry, Math 95 at City College. And this is a graph that is symmetric about the origin, because if we have a point and we look at the corresponding point that's 180 degrees away, both of those points are on the graph. You could even take a point here, go over 180 degrees. You can see that its reflection is there. You could pick a point, let's say, all the way over here, and you're going to have a point up here that's the reflection. So this is an example that is symmetric about the origin. Now we can't actually employ the test replacing x with negative x and y with negative y because we don't actually know enough in this class about how to deal with this sign that we can actually show that that's correct. But I just wanted to give you another example to show you that there's a lot of different graphs that we're going to see in this class, in trigonometry, in calculus, and the things that we're looking at now, like symmetry, are things that are going to pop up over and over again. So what we're doing is we're building a foundation that we can use to describe graphs that we see in the future and talk about similarities and differences.